Hi, my name is Przemek Uznański, and I want to talk about pattern matching in a stream under LP norms. This is a joint work with Tatiana Starykowskaja and Michał Swagerka. So, in general, text-to-pattern distance is a problem where we are given a text and a pattern and some general distance function. So in our setting, we are limiting ourselves to LP norms. So LP norms is a broad term encompassing, for example, Hamming distance or Manhattan distance, which is L1 norm, or Euclidean distance, L2 norm. But in generality, you can think about LP norms for some abstract parameter P. And the goal is to output for every offset. So for every alignment of pattern to a text, we want to output the distance, the LP distance, between the corresponding slice of the text and a pattern. So here, for example, for Hamming distance, we'll be in fact counting the Hamming distance between corresponding blocks of text and a pattern. So here we have distance 2, 3, 4, and so on. So the full array of those answers is the output of the algorithm. This problem has been already considered for more than 40 years. And it attracted a lot of attention in its classical offline setting. So here is the list of selected papers on either the exact problem, just for Hamming distances, or for approximation, so multiplicative 1 plus minus epsilon approximation of Hamming distances, or even just outputting Hamming distances up to some threshold value k exactly. And even if you go beyond Hamming distances and we just go to L1 norm or general LP norm, it attracted some attention, for example, for constructing approximation algorithms. But in this paper, in this work, we are considering the streaming setting, which is the setting encompassing the big data analysis. So here we are given a pattern, and instead of just a text given in a random access format, we are given text as a stream of characters. So our goal is after every new letter of a text arrives, to output the current distance of the last n characters of the text to a pattern of length n. So here we see that the more letters arrive for a text, and we have to output the distance of a pattern to a last n letters of a text. And the challenge here is that our goal is to use a small memory. So of course, this is doable if we just store explicitly the pattern, but our goal is to output, to use much smaller memory than n. And also the secondary objective is to actually be efficient, actually be fast. So spend little time updating our information and processing each new letter on a stream. So challenges of the setting is that while the streaming setting has been considered in generality already for more than 20 years by algorithmic community, we don't have a good understanding of how to perform sketching under sliding window. So classical sketches adapt poorly to shifting of window. Of course, in this particular setting, in the stringology setting, because there is a side area of this topic, which is actually considering a sliding window sketching, but it's a different type of sliding window. And another challenge is that many techniques that allowed us for constructing efficient offline algorithms are totally not applicable here because they use random access to a text, and they totally don't work in a setting of in a streaming sketching setting. So state of the art of this problem is that it has been actually considered 4 years ago at ICALP in the setting of Hamming distances and providing 1 plus epsilon approximation. So the actual results are that we can expect square root of n space and some polynomial dependency on epsilon on the space side, and on the time side is just some polynomial dependency on the epsilon for approximating of Hamming distances. And the dependency on epsilon has been improved by this year's talk paper by Chan et al. So original paper had epsilon to the 5 dependency on a space and epsilon to the 4 in time. And it has been improved to epsilon to the 1.5 space and epsilon cube time by Chan et al. And the work of Chan et al. Has been done in parallel to us. So we actually have a slightly worse space complexity. So there is epsilon squared space complexity, but we actually achieve a better time complexity. So we achieve 1 over epsilon squared time per each letter of the input. So those two results are uncomparable, and they actually rely on many different techniques, and the overlap is actually quite small. So I've been mentioning sketching. So what is a sketching? Imagine this simple communication complexity problem where there are 2 players, Alice and Bob, and they have 2 words, 2 inputs, or you can think of 2 vectors. And they want to estimate the Hamming distance, or not necessarily a Hamming distance, they want to estimate something, some function of those 2 words. So what they do, they, instead of sending each other those 2 words, they encode those 2 words, their respective inputs on some small space and construct sketches. So Alice constructs a sketch of A and Bob constructs a sketch of B, which are conceptually as small messages, as summarizations of the inputs. And then they send it to some third party, to a Charlie. And Charlie, just looking at the sketches of A and B, can compute some function of the inputs. So for our setting, it would be, for example, a Hamming distance. So how to actually achieve a Hamming distance? So now I will be talking a lot about, let's say, classical results or folklore results from the algorithmic community. So if we go not to Hamming distance, but we go actually to the Euclidean norm, to L2 norm, there is this classical result called by Alon Mates Szegedy, AMS sketches, where actually we can sketch a vector, input vector of length n by drawing at random coefficients from -1, 1. And this actually is a linear function, and it maintains in expectation the second norm of a vector. And by doing 1 over epsilon squared independent repetitions and averaging over those, we can actually estimate the second norm. And because it's a linear function, we can estimate the Euclidean distance. And why do we care about second norm? Where for binary strings, for binary inputs, all norms are the same. So particularly the second norm and the Hamming norm are the same up to a scaling factor. So with a little bit of hashing, we can also reduce general alphabet hamming distance to a binary hamming distance. And this allows us to easily construct a sketching for hamming distance, which takes 1/epsilon² space and provides 1+epsilon approximation to a hamming distance. Another technique, which is a little bit more combinatorial, goes as follows. There are efficient error correcting codes or sketching schemes which can sketch a word, and we can use those to actually detect whether a hamming distance between two words was at most k and then output it exactly, or just output infinity otherwise. And those sketches actually take roughly k size and k O of k time to compute the output, to compute the answer. So how do we actually go from this to approximation of arbitrarily large distances? Well, by sampling. If we sample 1/epsilon² positions at random, and the sampled positions are the same for both words, then we can just estimate by using error correcting sketches, by not knowing the exact size of the mismatches at sampled positions, we can estimate and approximately the total number of mismatches in general. And this is another folklore result, which gives us 1/epsilon² size and time processing for sketching. And why have I mentioned two totally independent techniques for sketching? Well, we will be actually using both of those. So let's look at some challenges for sketching in a streaming setting. So ideally, in the idealized scenario, what we would do, we would just look at a pattern, sketch it, and just keep the sketch, forget about the pattern, and then maintain some form of a sketch over a rolling window over a text. So whenever a new letter arrives, our goal is to append this letter on the right to a sketch and to remove the last letter that we are going to forget on the left, and so on. So in an idealized scenario, we would be having this black box where we could just append letters on one side and forget on the other side. And while such black boxes are possible, they require us to exactly know what we are forgetting. So that would require us to remember what letter we are trying to remove on the left side from a text. So that would enforce us to spend n, to remember explicitly n letters from the text, which is actually counterproductive. And this is a serious issue. So the better idea is to try to balance a little bit of memory usage between a pattern and a text. Because originally what I just described, we spent n space for the text and only almost a constant size for a pattern. And actually the intuition is that we could try to spend square root of n space for text and square root of n space for pattern. So what we do, we look at our pattern and we conceptually divide the text as it arrives into blocks, and the length of a block is roughly square root of n. And then if we look at what happens if a new letter arrives on a text, well, potentially we might need to create one extra new block. And we need to update some information in the last block that the window of a text encompasses. But apart from that, a lot of the blocks are untouched. So if we look at a particular moment of our streaming algorithm, and we look at how the pattern aligns with a text and particularly with the blocks of a text, we can distinguish three different areas. There is a suffix part, so there is this most recent part of a text, the potentially unfinished block of a text. There is a prefix part, which is the last block, which doesn't even have a full overlap with a pattern. And there is the middle part, which are all of the blocks that are not the prefix and or not the first and the last block overlapping, but all of the middle blocks. And those are almost all of the text in full blocks overlapping with a pattern. So we'll deal with those separately. For the suffix part, the idea is, I mean, this is the most recent part of the text. So we can store explicitly. This is one approach. Store explicitly the square root of n letters, the last square root of n letters of t in a string. And also we can afford to store the last square root of n letters of p always. When we are pre-processing pattern, we just do it. We just store it. And then all of the queries for the suffix part, so all of the mismatches for the suffix part can be computed exactly by spending square root of n memory, but unfortunately, we also need to spend square root of n time. And the memory usage here is even better than what we are hoping for, but the time is suboptimal. So what we can actually do is instead of storing explicitly those letters of a pattern, we store sketches of suffix of length 1, suffix of length 2, up to suffix of length square root of n of a pattern. And then we maintain a rolling sketch of the last block, these suffix blocks of text, t. What this allows us is whenever a new letter comes, we just append it to the sketch of a last block of the text t. And we compare this sketch with corresponding sketch on the pattern side. So if we just started this block, we compare it with one suffix, and if we are finishing this block and it's of length square root of n, we compare it with square root of n suffix. And potentially every once in a square root of n steps, we need to restart this sketching procedure. So this actually expands the memory complexity a little bit to square root of n over epsilon squared. But the time to decode is just comparing two suffixes, which is 1 over epsilon squared. For the middle part, there is always a part of a pattern of length roughly n minus square root of n, which overlaps fully with the middle part. So what we do, all of substrings of this particular length of a pattern, there are roughly square root of n of them, are sketched and stored. And the goal is that instead of remembering the exact content of the blocks of a text, we will remember only the sketches of those blocks. Sketches will be much smaller. So just by looking at the sketches of the middle part blocks, we compare them with a sketch of the corresponding substring on the pattern side and compute our answer. So the challenge here is that on the text side, we can afford to maintain short summaries of sketches, short summaries of blocks of length square root of n. On the pattern side, we have summary of all of those corresponding parts concatenated. But if we could find a way to actually compare those two together, that would be very efficient, because what it actually forces us to do, it forces us to sketch each block of length square root of n on a text site, and we can afford it because there will be only at most square root of n such blocks. So the memory is square root of n over epsilon squared. And hopefully we could achieve the time complexity 1 over epsilon squared. So the key idea here is that if we have Alon Matthias Szegedy type sketches for several words, we can perform once again the same procedure and do a sketching of sketches, which would be like a meta sketch. And for the details of the construction, see the paper of Crouch and McGregor from approx 2011. But it means that if we have the sketches of blocks one after another, and a corresponding sketch on the pattern side that encompasses them all, we can actually extract the distance between those two parts. And the most challenging part is the prefix part. Here, we have a block of a text. We totally forgot what was there, because it's the last block. We really cannot afford to store explicitly the letters that were encompassing of this block. And we have a pattern that is overlapping a little bit, but not fully with this text. And we want to query what is the approximate Hamming distance on the overlapping part. And here really we have to fight with the fact that the queries might be of arbitrary overlap. I mean, right now we are answering for this particular overlap. In the next step, we are going to answer for the overlap one shorter, and so on. So a sub-problem that we can single out here is that we have a block of a text T of some short length, and we want to support a prefix-suffix approximate distance queries. So we have a block, and we want to store in a compressed fashion this block, but to support the queries of prefix-suffix queries between this block and a pattern, and a prefix of a pattern. The advantage that we can actually use is that while we cannot afford to store the content of the block, we need to compress the block, we can afford to store explicitly the first square root of n letters of a pattern. So the pattern is always the same. It's just that the blocks are changing. So what we actually propose is to go into to use subsampling. So for each power of 2, so 1, 2, 4, 8, and so on, we pick at random r positions. So for each value of r, it's done independently. And then while we are still preprocessing, while we are holding this block in our hands and we are still doing some preprocessing, what we can do for each value of r, we look at the maximal overlap, maximal possible overlap between a prefix of a pattern and this block, that it generates at most epsilon to the -2 mismatches on the selected positions. So we ignore the grayed out positions in a block and we only look at the yellow parts. And what we do, we store explicitly the length of the overlap. We store explicitly the mismatched positions together with what was the actual mismatch, what were the mismatched letters. And we store this length square root of n prefix of a pattern. But this is shared among all of the preprocessed blocks in this position. So the length of this maximal overlap and the mismatched positions, it's 1 over epsilon squared per block, and there will be at most square root of n different blocks in parallel. So we can afford this. And then in the future, when the actual query comes, and we have this information stored, our claim, which is a little bit technical claim, but you can find the details in the paper, is that for any value of R and some overlap query, so there's some query on the overlap J, if J is larger than the length of the maximal overlap at this actual level of sampling, we can recover the necessary sample letters from the block and then compute the number of mismatches that were between the actual query and the block. The number of mismatches between the actual query and the block on the sampled positions, or decide that the number of mismatches was too large. What does it mean? It means that if we look back at how the sampling algorithm is used with respect to estimating the Hamming distance, we can estimate the Hamming distance on the overlap with 1 plus epsilon approximate error in a space which is 1 over epsilon squared, space and time. And because we'll be maintaining square root of n such compressed forms for each block, and there will be square root of n blocks, it means that the space complexity actually blows by a factor of square root of n, which is what we actually were aiming for. So to conclude this talk, I advertised that we are also dealing with other norms, other LP norms, and I'm compelled to say that we are using a mixture of old and new techniques. So we are using because these sampling techniques and so on are not fully adaptable to other norms. So we are using p-stable distributions for sketching of other norms. We are using range summable hash functions for L1 norms. And we are also using randomized embeddings of LP norms into Hamming norms to deal with some partial results. So we believe some of those, we believe the randomized embedding result is of independent result, independent interest. And actually, maybe to tease a little bit, we are sure that the story of this problem is not fully closed, because the best results that we got, we were able to get, those are the best complexities that we were able to squeeze from. But we believe those could be improved. So while we know the space is suboptimal, we know square root of n over epsilon to the 1.5 can be achieved for Hamming distance. We don't know if it can be achieved for other norms. And the time complexity for some other norms is truly to be improved. So many open questions, many open avenues for the attack. Thank you.